Okay, so I think we're live now, and in that case, I'll start. So my name is Jonas, and as you may know, I'm based in Stockholm, Sweden, and today I'm presenting the GMW protocol for secure multi-party computation. Just to give you a bit of insight into the history or the context around this paper, it was published in 1987. And this is only 1 year after the Yale's garbled circuit publication, which was in 1986. So as far as I know, this was the first secure multi-party computation protocols for multiple parties, whereas Yale's garbled circuit was only for 2 parties. And so this is an overview of what we're looking at today. We're looking at the problem of computing a binary circuit in a secure way, namely that we're supposed to keep the privacy of the various inputs and keep that in mind, but also the correctness of the execution. And it should be correct and private, or adversaries, or rather the adversarial model that we consider is the semi-honest model. So an adversary does not try to corrupt the protocol, rather follows the protocol, but an adversary tries to learn information from the exchanged messages. And we want, or it's also secure up to n-1 corruptions, where n is the number of participants or parties that we have in our protocol. We make 2 assumptions. We assume that we have some form of private channels, so the parties can privately message each other. And we also assume that we have this 1 out of 4 oblivious transfer functionality, which I'll also describe in a few slides what it is. And on the right-hand side of the slide, I have just a bit of a visual for what we're doing. We have this ideal functionality that we're trying to emulate that computes a binary circuit, and the binary circuit we can compute consists of 3 gates and not an XOR gates, and you can show that it's sufficient to have only AND and XOR gates to compute any possible binary circuit. So with this, we can compute any possible binary circuit with the solution I'm presenting today. These are just some of the notation that I'm using in this presentation. So we'll write something like P_I to signify that party with index I. When I write X like that, it's a plain text value, and X with these brackets around it is the secret shared value of X. And when we have something like this, X and _I it signifies party I's share of the secret. Continuing, we have here just a way of sampling a random element from some set of elements, and we also have the XOR symbol, which you'll see a lot in this presentation. So this multi-party protocol also works on secret sharing, on the basis of secret sharing, and we're using a additive modulo 2 secret sharing on binary values, on bits, that is. So our plaintext values are 0 and 1, and also the secret share is also only binary values 0 and 1. And to get the plaintext value, all we need to do is take the XOR of all our secret shares to get the value back. And if there are any questions, please just ask away. I hope the slides are easy to follow. Otherwise, go ahead and ask. Okay. Oblivious transfer is maybe something that we haven't covered yet. There are 2 parties in oblivious transfer. We have a sender and a receiver, and the sender in this case can choose to, or rather chooses 4 values that it would potentially send. And in this case here we have x0 to x3, and the receiver can choose which of these values to receive. So the output from the oblivious transfer is the value that the receiver chose to receive, and the security of the Oblivious transfer, there are two things that should hold. On one hand, the sender should learn nothing, including the sender should not learn anything about the choice from the receiver. So the sender does not learn what S was. And the receiver should only learn about his received value. And in particular, the receiver should not learn anything about any of the other values. So if we can implement something like this, we have 1 out of 4 Oblivious transfer. Okay, so similarly to the other protocols that we have looked at so far, we have 3 steps in our protocol. The first step is that we share the inputs, and in the second step we evaluate the gates on these shared inputs or in the secret shares, and in the last step we reveal the secret shares to the parties. And I'll look at each of these steps now separately. So to share inputs, it's rather simple using this secret sharing scheme. If you look at the case for party I, and party I wants to share an input X with all the other parties, how does he achieve this? Well, party I samples a random bit for each other party J and sends this random bit to party J as their secret share of X. Then to compute party I's own secret share, party I computes the XOR of plaintext value and all of the other secret shares. And this is correct because, well, if you just write it out like this, these are all the secret shares that we have, and we XOR them together. We get this, and then we replace our xi with the expression there. And we see these two terms cancel each other out. So indeed, we get the X value back. Okay, so now we're starting with the evaluation of the gates, and XOR and NOT are the two simple cases because they don't require any interaction. Whereas the AND gate will require interaction. So we can start off by looking at the XOR gate. We have the two inputs X and Y, and we want to output a secret sharing of Z, which is the XOR value of X and Y. And the way we can achieve this is that for each party I, the party can simply take the shares it has locally of X and Y and compute the XOR of those values and get the new value for the new secret set. So that's pretty easy to do. And as I said, no interaction. For the NOT gate, we do it somewhat similarly. So here we have input X and we want to output Z as not X. And all parties can use their value of the X share as their new value of the Z share, except for one predetermined party, for example, party 1, which can just take the value of not X as its new Z share. So in the end, when we compute the plaintext value of all these Z shares now, we would just have an additional operation of, or the effect is that we flip the bit, so it's it's still correct. Sorry. Okay. Any questions so far?
So I have a question. I think it's related to the previous slide. Does it work in a scenario where there is a user which is not part of the group performing this protocol? Can the user share his own secret among the group? So no one in the group actually knows the secret, it's just shared, and can they compute based on the user provided secrets?
Okay, so a user you're saying a user,
yes, say
or
there's
rather like a client
nodes.
that is not part of the computing servers in this case. No, I think let's say we have let's say we have 3 servers, right? And we have a client who then shares the value with the 3 servers. I guess it would work if we have up to 2 adversarial servers, then we can run the protocol. Yeah, that should work, but I don't think it works for the case when we have 3 adversarial servers.
Of course, I mean, if all servers are adversarial, nothing is going to work. What I was asking is if we have n servers out of which up to n-1 are adversarial, and the user which is not one of them, and the user just wants to provide the input by sharing it among the group. And are they able to perform computation using this protocol with such shared secret, even though no one in the group knows the secret? They have only the
yeah, I think so. So as we see here, we're not using any plain text values. So the client can create all the secret shares and distribute them. And for no XOR and NOT, we're not using any plain text values, so the server should be able to compute this. And I think when we look on the next slide, if I'm not wrong, there are no plain text values used either. So that's a good continuation. So we can have a look at the AND gate. And here I'm just trying to prime you a bit on the AND step, because the AND gate is the complicated gate out of the 3. And at the bottom, we're just answering Adam's question. We can look at what each secret share looks like for each of the parties of the new value set, which is the AND of X and Y. And we see that we don't use any plain text values, and for any of the following slides, we don't have plain text values. So this should also work in the setting which you described. Okay. So let me now prepare you for the next 2 slides by showing this. So if we want to compute Z as X and Y, and we replace X with the XOR of all its secret shares, and Y with all its XOR of all its secret shares, and then we expand the expression a bit, we come here to this 4th line, and we can see how can now or what kind of terms do we have? Well, so these terms, for these terms, I equals J, and so each party can compute these terms locally because they have both I and J. But the problem is with this term, where we have Xi and Yj from 2 different parties, and also Xj and Yi from 2 different parties again. So for this term, we need some kind of interaction. And we want also, and what we'll discuss is a solution using the Oblivious transfer. However, the difficulty with Oblivious transfer is that you have the sender and receiver, and the sender chooses which values it wants to try to send. But the sender doesn't know, for example, what Xi is or Yi is if the sender is J. So in this case, let's imagine that the sender is J, and he wants to send this expression, but he doesn't know what Xi is or Yi is. So we need to figure out a way of how we can achieve this. And so if we look at the next line, this is a bit of a preview to how we'll do it. The sender will choose some kind of bit mask, and then the sender will be able to somehow compute this for the value it sends. And then the receiver will also, or rather the sender will later also add its bit masks to the XOR of the whole thing. Anyways, let's continue and we'll have a look. And so if these are probably the most complicated slides, these two. So if there are any questions, go ahead.
So the bit mask, is it going to be known by sender, receiver, or none of them?
You can see here, so you'll know it in just a minute. The way the protocol works now for party I is that party I basically does for all other parties j that are larger than I. So if I is smaller than j, then I is the receiver of this oblivious transfer, and party I receives this expression, but as a single value. So I've written out the whole expression now, but we only receive a single value from the oblivious transfer. And if I is larger than j, then I is the sender, and the sender receives the bit mask from running the oblivious transfer routine, which I'm describing on the next slide. Such that in the end, if we're taking the XOR of all these values, the bit mask cancels the other bit mask out. And then the way we set the secret share is to simply say that the new secret for the new set is take the AND values of our two local shares that we have, and then we take all the received values in this expression here. These are all the received values from the oblivious transfer, and then all the sent or all the bit masks that we received from the sending routine of the next slide. Okay, and here I'm hoping it becomes clear now. So please ask questions if it's not becoming clear. But the important part of the protocol is how can we, how can the receiver receive a value that the sender doesn't have? Or rather, how can the receiver receive some value which is computed by the xi that the receiver doesn't have? And the way the authors had a nice idea to make it so that the receiver puts as an input to the oblivious transfer the values of xi and yi, such that if the receiver puts the values 0 and 0 for the shares it has, it would receive the first term. And if the receiver puts 1, 0, so xi is 1 and yi is 0, then it would receive this term. And that's how we can make it so that the receiver receives this value. The sender basically first gets a random bit mask and then computes the XOR of this bit mask and this expression on the right, where he has his own yj and xj value. And also, because he knows that if the receiver wants to receive this value, the receiver has 0 as a secret share for xi and 0 as a secret share for yi. And if the receiver wants to receive this value, the receiver has 1 as xi and 0 as yi. So that's how we send the correct data to the receiver. Well, we can think of the security of this. So why is this now secure? We have to ensure that the receiver, on one hand, does not learn anything about the shares of the sender. And we have to ensure that the sender also does not learn anything about the shares of the receiver. This is where the properties of oblivious transfer come in. The receiver only learns about this value that he receives and nothing else. And because the receiver, or rather the value, is masked by this bit here, a random bit, and the receiver doesn't know what random bit it is, the receiver has not learned any information about what's in this expression here. And for the sender, it's the same. The sender does not learn anything from the protocol. The only thing the sender gets out from our routine here is the bit mask. So the sender later on can use the bit mask to offset for his own shares. All right.
So the outcome of this is that they both get outputs which sort are giving the expression that is needed, right?
Exactly. We can look at this slide again. So the receiver receives this value, and the sender gets this value, and then these two cancel each other out, right? This bit here cancels this bit because it's the same random value, and then we end up with this value here, and we just add them all up again. Was that clear, or?
I think it's pretty clear for me.
Okay.
So can I have another question?
Mm-hmm.
So I'm confused. Why do you need 1 out of 4 Oblivious transfer instead of doing it with 1 out of 2 Oblivious transfer? So when you have this expression, this xi XOR yj and xj XOR yi, then you can further break it into, you know, just pairwise ends, like xi, xj, and yj yi, right?
Isn't it the case that a single 1 out of 4 Oblivious transfer is just more optimal than 4 different 1 out of 2 Oblivious transfers?
Yeah, I'm wondering. I think you could definitely use 1 out of 2. But maybe it's more the case where you're sending, in that case, you're sending 2 values across instead of just sending one value across. And I guess you would also have 2 of these random values you need to keep track of instead of 1.
Yeah, I mean, that's possible, definitely. But yeah,
it
would be kind of surprising to me that these guys who are mostly concerned about theoretical, just a theoretical protocol would actually make it more complicated just to gain 2 bits. So yeah, that's what I'm wondering.
Yeah, I don't have a good answer. I mean, it makes the protocol slightly shorter because you only have 1 Oblivious transfer, but we can think about it. Okay. If there aren't any more questions, I'll continue. So now we're reaching the end phase, and we have computed all the gates, and we have all the outputs from the gates as secret shares. And so the last step is to reveal the outputs to all the parties. And the way we can do this is quite simple. So party PI would announce its shares to all the other parties and wait for the shares from all the other parties, and then just tally them up and compute the plaintext values of the output. So we can think of the performance in this protocol. And there are 2 important things to consider. One is the number of rounds, and by rounds, and so the number of rounds is lower bounded by, I hope this is understandable, the most amount of AND gates in a path of the circuit. You can think of it as your sort of flooding the circuit from the inputs to the outputs. And every time you reach an AND gate, you have to at least initiate a new round. So this frontier can only advance as far as the AND gates are. And thus you have to at least have as many rounds as you have AND gates in every path or in one of the paths. And another performance aspect is the number of Oblivious transfers you have to execute. And this is the bottleneck of this protocol. We have to execute n squared times the amount of AND gates, number of Oblivious transfers, roughly. And so that's definitely where we need to, look in order to optimize the protocol, which leads me on to, some follow-up we can maybe discuss in the next sessions or so. One thing to consider is exactly this Oblivious transfer, how to make it more efficient. And there's some nice, or it's called the Oblivious transfer extension that is a lot more efficient than the basic OT or the standard Oblivious transfer that you would use. Difference here, I can give a preview. The difference is in the basic Oblivious transfer, you would need one public key encryption per transfer, whereas in the Oblivious transfer extension, we can use something like 128 instances of the basic Oblivious transfer to bootstrap up to 1 million or so Oblivious transfers in the Oblivious transfer extension. So we can make it a lot more efficient through that way.
So this is kind of a preprocessing, but you can do some preprocessing to have something which will allow you to make million cheap Oblivious transfers. Is that correct?
Yes, on one hand, you could do it in pre-processing times, but also for each basic OT, you would need one public key encryption, but for each 1 million OT extensions, you would only need one basic or 128 basic OTs. Something like that is the idea. So you just also reduce the amount of computation you need to execute on each computer. And yeah, so these were the references. Also, this was a great video from the EIU Winter School, and those are some good references, and those are also some good lecture notes I used to prepare this presentation. And that's all. I hope you enjoyed it, and also if you have questions, maybe some immediate questions for understanding the content.
The immediate will be that you, I think, skipped one dot. You had 2 slides before. You had a dot on malicious version of GMW. So can you make it work in fully adversarial? I mean, not semi-honest, but normal adversarial scenario?
Can you? Yes. So one of the references talks about how to make it in the malicious setting. So we have to consider the protocol I presented today is not malicious. On one hand, you have to ensure that I think you have to commit on the input values similarly to the speeds protocol we discussed last week, for example. So those are some things that we also would need to consider here.
But being able to verify the correctness of the result is one thing. The other thing is, can the nodes learn anything by being just malicious? And how could they do this in this version?
There are 2 answers here. One answer is that you can always do that because there is this general compiler from any semi-honest protocol to a malicious protocol. by using essentially lots of zero knowledge proofs. So yeah, you can look into that by just going to the book. So there is this Oded Goldreich's book, and it explained this compiler in detail, but it's not very pleasant. So that's one answer. In theory, you can do that for every semi-honest protocol. And the second answer is, yeah, even though you can do that in theory, in practice, it's not that good because the compiler is very inefficient and it's actually very bad. Like the protocol you get is very bad and it's super heavy. So yeah, I guess there are some versions of this which are more practical.
What's even more interesting for me is not how to fix it, but what's broken. I mean, which part of this protocol is not maliciously secure? Because, like, of course, the local steps are okay. So the only thing where the adversary could steal something, I think, is this protocol, the Oblivious transfer protocol. But this is a separate primitive. So is it the case that if you make 1 out of 4 Oblivious transfer work in fully adversarial scenario, then you are also making this whole protocol work this way?
Right, probably. It depends how you formalize the Oblivious transfer functionality, I believe, because you can have. Yeah, I'm not sure about that.
Or maybe the malicious party could lie about its inputs during the Oblivious transfer and put all of the possibilities here. Oh no, sorry, I retract what I just said.
So normally, like the hard thing would be, okay, so let's say they commit to everything, but then you also need to connect these commitments with the Oblivious transfer protocol. So like plugging in a black box maliciously secure Oblivious transfer is not that easy because you need to this needs to work with the commitment scheme or whatever you use to make sure everyone uses the same inputs and does not cheat when doing XOR or negation or stuff like that.
If you black box zero knowledge, then you can always say that, well, yeah, I prove in zero knowledge that this black box.
Yeah. So this is the compiler then, which allows you to do everything, but yeah. So yeah, the thing is that in this slide, PJ can just pick some X. So these X's like X00, X01, X10, X11 can just take whatever values here and use them for this Oblivious transfer. And
so when the output is revealed, it can reveal something about the inputs if these values are specifically prepared for this, right? That's what you are saying. For example, if adversary would control n-1 nodes, and in all Oblivious transfers that it is involved in would put only zeros, and all of its shares would put as zeros, then the final output, I think, would reveal something about the shares of the only honest party.
Yeah. Yeah. So essentially, yeah, it's not so clear to me, no, but one can start by thinking what happens if there is no randomization here. Oh, okay, this randomization is just so that the sharing is random.
No, just consider a circuit with a single AND gate and n-1 adversaries. So they all lie about their shares. They lie that they all have only 0 valued shares. So then everything in the output will cancel out, despite the with the exception with the I think end of the only honest party shares. So the adversary will learn what's xi plus yi was, where I is the index of the honest party. If you do not have a commitment.
Yeah, something like that. Yeah, that's correct. And they can just keep this knowledge to themselves and not reveal later. So only they learn it and the protocol is aborted.
It's not quite clear. Kev sent something in the chat. For just say here, malicious GMW.
Actually, this compiler, I think the idea of this compiler is coming from the same authors as the protocol, right now.
I'm not sure the set is exactly the same, but maybe. Yeah, some names definitely match. I don't remember the full set. Yeah, okay, yeah, this is a GMW compiler. Yeah, sure. This should be the same.
And does anyone know what's the like? Is it practical using the modern Oblivious transfer implementations? By practical, I mean like speed.
Do you mean if GMW is practical?
I mean, if you put a modern Oblivious transfer implementation.
So I think that nothing which has semi-honest in the model is practical because it's not very useful. But then if you transform it into maliciously secure, then other things become the bottleneck, I think. So you can use this Oblivious transfer extension, which is like super fast to do Oblivious transfer. But
so what you're saying is that would be fast, but not very useful because of
I think so. That's my that's my perspective. That if you just get Oblivious transfers, then as Jonas said, it's you just use Oblivious transfer extension to have lots of Oblivious transfers very cheaply, and you can do that. So then this is a quite good protocol. but I'm not sure this is enough if you want maliciously. So,
Yeah, how does it compare to the BGW again? Performance-wise, I think we have the same amount of rounds, right? So for every multiplication, we have to have a round, pretty much. Then for the number,
yeah, I think it's pretty much the same. Yeah, I'm pretty sure it's the same complexity.
You mean communication complexity should be the same?
Yeah,
When it comes to the amount of computations, this one is probably faster due to the super modern OT.
Although, yeah, this.
I don't know. I mean, there's a lot of depends on n probably. If you have like large n. So what's the complexity of BGW? Does anyone have it?
I really don't like the fact that all these protocols have 3-letter acronyms. I mean, this is super misleading.
So for one multiplication, you need to each party needs to share a secret. So you would also need order n square communication for the other protocol. But yeah, there is this additional requirement that the number of malicious parties is less than n/2, right?
Yeah.
Here you don't need that.
Well, I think you could run the BGW with this this secret sharing scheme as well, I think. Then threshold would be the same. Right, it's only it's sufficient to have a linear secret sharing scheme. I think this one is linear or semi-homomorphic.
Running BGW for Boolean circuits instead of arithmetic, and
yeah,
I think that.
Yeah, multiplication is XOR, and or no, multiplication is
multiplication is AND, like the hardest gate.
Yeah, sorry, yeah. Yeah, and addition is XOR in that case. Yeah, that would should work.
Yeah, it makes sense that the hardest gate is the same, and even the protocol to solve it is pretty similar, actually.
I guess the BGW, maybe why it's more practical is you do all the work in the pre-processing or most of the work, whereas here it's like we do every AND gate and then we can't do any pre-processing, or maybe there is a way of doing pre-processing.
That's actually an interesting question.
Right?
Could you generalize the Beaver triple idea to work with this protocol? And my bet would be that yes. You should be able to.
Yeah, you can do that. You can do it for every secret sharing scheme which is additively homomorphic, and yeah, additively homomorphic is enough, and you can reveal. You can, yeah.
Mm-hmm.
What's probably a big difference when it comes to practical applications is that in general, arithmetic circuits are probably way more practical than Boolean ones. I mean, if you have a protocol with roughly the same execution time which can compute arithmetic circuits, you would rather use that than the one computing the Boolean one. They are more expressive, I guess. Although
I don't know, like
yeah, I don't know either.
because you could have you can have unsigned integer, right?
It. Sorry?
You know, like an unsigned integer as a sort of a vector of 32 bits.
Mm-hmm.
You know, and then how we can do XOR locally, like treating every bit separately. Multiplication, that's tricky.
Sure,
yeah.
I mean, you can translate it, but the circuit will be bigger after the translation, I think.
So my impression is that any reasonable computation you would like to make, you actually need to decompose into bits anyway, because like any comparison and like equality check is actually fine, but like, yeah, what is a reasonable program you can write without any comparisons? Like, you know, less than, you cannot, I don't know.
Yeah.
Okay, perhaps you're right.
So yeah, my impression is that whatever reasonable program you write, you want to compute it using MPC, and the translation to a circuit will necessarily go through decomposition into bits anyway. I don't know, but that's my feeling. And then, yeah, it's not clear whether you can gain anything by using arithmetic circuits.
Especially if you're interested in making some kind of a general framework to write programs, then it should be default to decompose. So
yeah, but maybe the default should be, or like you have a hybrid of the two. And the question,
yeah, so like, there are these
can you
approaches.
go from like efficiently now? Can you go from this binary or bit sort of view to like the Shamir secret sharing scheme and back? And is it an efficient way of doing that?
Is it the case that when it comes to this translation, there is like a pragmatic approach where you define which inputs should be converted to bits and which should not? Damian mentioned that there is
maybe
like
you can do something
approach.
like that. I am aware that there are some works about this hybrid approach, also for zero knowledge proofs for snarks. And this is actually, one way they are trying to make this efficient, much more efficient than just like, just using binary or arithmetic one type. So this can be a reasonable thing to do, but I don't know how it works. This hybrid thing.
I don't think I have more questions. Do we know what do we want to see next week?